the lab report for Lab 1 on constant velocity. The purpose of the lab is to show that a system at constant velocity is at constant velocity if there are no forces acting on it. This means the system, in this case the marker, will stay the same speed throughout the entire time span. The main principle in this lab is Newton's second law, the momentum principle, which says that the system's velocity will only change if a net outside force acts on it. In this lab, we use the tracker software to video the marker being rolled and measured the change in position and change in velocity of the marker relative to time. We also use code on GlowScript to model the rolling of the marker and predict how the position and velocity would change. Both the observed velocity and predicted velocity were shown as constant after plotting the data on the graph. This is because the net force on the marker was 0. The most important principle for this lab was the momentum principle, and it states that the change in momentum equals the net force multiplied by time. This means that the momentum stayed the same when there's no net force, and unchanging momentum means the velocity remains constant. As the marker was rolled on the table in this lab, there was no outside force, meaning the marker rolled at a constant velocity across the table. This means that if you plot the marker's position versus time and its velocity versus time, the position versus time graph will be aligned with a constant slope, and the velocity versus time graph will be aligned with a slope of 0. To do this lab, we assumed that the net force was 0 and that the friction was negligible between the marker and the table. The tracker software output showed that the position was changing at a constant rate, meaning velocity was constant. We only focused on the x-axis because the y-axis, it would have just been a mistake. Any change in the y-axis was a mistake because we only rolled it in the x-axis. The in time from the tracker observation was 0.434 seconds. That's why we the loop ended at 0.434 seconds for the code. The initial position and the velocity for the marker was 0.0109 and 0.731 respectively, and that is shown in the code to set the initial. The net force was assumed to be 0. That's why we made the force vector 0 in every single direction. The velocity update formula and position update formula were used throughout the code to predict the position and velocity of the marker. Okay, and the tracker software outputted the data where velocity was constant because there was a constant slope for position versus time, and the velocity versus time was a horizontal line. For the observed velocity and predicted velocity were pretty much the same the entire time. This is shown by the graph, which has both position versus time lines having the same slope. However, the observed line does increase with a greater slope than the predicted in the beginning. It then becomes the same slope and then decreases at the end. Possible sources of error could be a slant in the table in the beginning and friction between the marker and the table at the end. Additional questions: what if the negative x and positive x axes were interchanged in tracker? If the axes were flipped, the tracker would have shown a constant negative velocity. And what does it mean? What pull and push forces canceled out to net a force of 0? This would have been the normal force, which was the table pushing up on the marker, and the and gravity, which was pushing down on the marker. And friction was assumed to be negligible.